So thank you everyone for coming here or logging into Zoom to see this talk. So usually we have someone presenting the speaker, but obviously this office is a little bit too small for the 1 person per 4 square meter thing. So I just have to introduce myself. So I'm Matias Quiroz, and I'm a lecturer at the University of Technology, Sydney. I'm also an associate investigator of ACEMS. And today I'm going to give a talk on some recent advances in our work. The title of this talk is Recent Advances in Subsampling MCMC. And it is actually a follow-up talk on something that I spoke about during July 2019. So during July 2019, I gave a talk that was entitled Subsampling MCMC, Bayesian Inference for Large Data Problems, or something like that. And this talk is gonna build on that talk. So today we'll cover some recent advances, and also, of course, if you've forgotten the talk from July 2019, I'll also talk a little bit about the methods that we're using, just I hope, on an introductory level. So this is the crew that I'm working with. In alphabetical order, I'm highlighting some changes. The first big change is that KD Dang is now Dr. Dang. She graduated February, so she's now a PhD, and she has joined the University of Technology, Sydney, which I'm, of course, very happy for. And then we also have a new crew member, Robert Salamoni. He's doing his postdoc with Robert Kahn at the University of New South Wales. So what's new today? So there's a paper that's new. This paper didn't exist when I had the talk last year. And the title of the paper is Spectral Subsampling MCMC for Stationary Time Series. And there's 2 key contributions there that I want to highlight. The first one is that we have improved the control variate constructions. I had a very good question last year on what do you do if the control variates are not, if the models are a little bit more complicated, and we now have a way of addressing that issue. And perhaps even more exciting is the second point here, because what we have been doing, as you'll see during this talk, is that the methods that we have developed so far, they have only been able to handle conditionally independent models. So when you have that your data conditionally on your parameters are independent, then our methods have been working very well. But this is, in this paper, this is a first extension beyond that case. And finally, there's new results that emerged during a revision on a paper that I actually presented last year. So we're revising this paper, the block Poisson estimator for optimally tuned exact subsampling MCMC. And we have some very interesting results that we're gonna send up to archive in hopefully a couple of days. But this is the first time I'm showing these results to anyone outside our research group. So if you wanna follow, I put the slides here. I was going to put them on Twitter as well, but then when I got to the office, my university shut down the air conditioner, and my fan here that I bought was broken. So I spent like 30 minutes desperately trying to fix it. Luckily I did. So I have a cooler here that blows on me, so I don't get all sweaty. All right, let's get to it. So the motivation of subsampling MCMC is that, first of all, we know that MCMC is perhaps has been the Bayesian workhorse for 3 decades. It's a very important algorithm for Bayesians that allow them to sample from the posterior distribution. However, this algorithm is often slow. The main reason is that you need to evaluate the likelihood function in each iteration. So for each sample that you want to obtain, you need to evaluate the likelihood function. And these samplings algorithm, you typically need a lot of draws to get a picture of how the posterior looks like. And for each of these draws, you need to evaluate the likelihood, and that's very costly. And in particularly so when you have large data sets, right? Because this likelihood function is going to be a function of this large data set. You need to evaluate over and over again. Subsampling MCMC, the idea is super easy. So what you do is that instead of evaluating the likelihood function, instead of evaluating this guy, you're going to take a subsample of the data in each MCMC iteration, and you're going to use that subsample to estimate the likelihood of the full data. So from the little subsample, you estimate the likelihood of the full thing. So of course, like just this bullet point here, it's a pretty simple idea. The idea is really straightforward, but it's actually a very hard problem to solve. And we have spent many papers on this and thinking a lot about it. But the key thing in the whole approach is that we utilize something that's called pseudo-marginal metropolis Hastings. So pseudo-marginal metropolis Hastings, see if you know about metropolis Hastings, pseudo-marginal metropolis Hastings is just a metropolis Hastings on an augmented space. So theta is usually the theta here is the model parameters that you usually care about, and these U's here are going to be sort of like artificial variables. I'm going to explain a little bit more about the role that they play. So in usual Bayesian inference, what you do is that you want to obtain samples from the posterior distribution here, which by the Bayes' theorem is just proportional to the likelihood of the model multiplied by the prior other parameters. So instead of sampling from this thing, we go and sample on the augmented space. So we augment this here, and we construct an artificial target density. So it's a density of the thetas and this artificial U's here, and that's going to be proportional to. And notice here that I had replaced the likelihood by this little funny symbol here. So P, and I put a hat on it, and then I have my U's here. So this is just the estimator of the likelihood. So this guy here estimates this guy here. And the randomness in this estimator comes from these U's. So now you understand, like these U's, they play the role of being the artificial random variables that are used to obtain your likelihood estimator. Okay? And then you have a joint prior of the theta and U that you assume factorizes like this. So if you've seen the metropolis Hastings algorithm, you will quickly notice that whatever is in this box here is just a metropolis Hastings algorithm, but on the space here, on the augmented space. So you'll see that you'll sample capital N iterations, you start somewhere, and then you make a proposal for your parameters, you make a proposal for your random variables that you use to estimate the likelihood, and then you construct an unbiased likelihood estimate. So the likelihood estimate here has still the same symbols as up here, but the P here denotes the proposed value. Okay, so you propose a value of theta and U, and then you decide if you're going to accept the proposed values or not. And for that, you compute this metropolis Hastings acceptance probability here. So you see that, like, if you just assume that we would have a symmetric proposal, so this guy here doesn't exist, assume a uniform prior, so these guys here don't exist. The only thing you're doing actually is that you're evaluating the likelihood at the proposed point and at the likelihood at the current point. And if the likelihood at the proposed point is bigger than it is at the current point, then you will move there with an acceptance probability that is 1. Otherwise, you're going to move there with an acceptance probability that's this ratio here. Okay? So with probability alpha, we set the state of our Markov chain to be the one that we have proposed. Otherwise, we just let the Markov chain stay where it was in the draw before. So if you have an unbiased estimator and you do this, and you just at the end you just discard your U's, you don't care, so you marginalize the U, you don't care about them, and you look at the distribution of the thetas, then asymptotically you will actually sample from the marginal that you wish to sample from. So notice that this is a quite cool thing happening here. You're never actually evaluating the true likelihood, you're only estimating it, but under this unbiasedness condition, the draws of theta actually come as if you would compute the true likelihood. You're targeting the same thing at the end. This is true for any positive unbiased estimator. However, of course, the variance of this guy is going to be crucial. And in general, we can say that the smaller the variance, the better. There's a little bit more to it, but for this talk, it's okay that you need to understand that you cannot just go and estimate this with a lot of variance. I'm going to keep things simple here. I'm not going to go too much into details because it's just we're just recapping what we talked about last year, and I went into much more detail in that case. But here, my idea here is just to show you the recent advances, so I'm going to skip that. Okay. Okay, so how do we actually do this? So we have an old paper. It's not so old. It was published last year in JASA, where we propose to use a bias-corrected likelihood estimator, and that likelihood estimator is based on being able to estimate the log likelihood unbiasedly. So I'm just going to see if there are any hands here. I haven't looked for a while. No hands. The chat seems okay. All right, sorry. So notice here that I've changed like the notation here. So this L here of y given theta is going to be the log likelihood of the model. So assuming that I have conditionally independent data, we know that it's just a sum, right? So it's just a sum of the individual log likelihood contributions. Now I want to estimate this guy by putting a hat on it, and this is the form that I'm going to have on my estimator. So I'm going to take a subsample of the data. So the U here is just the indicators, the subsampling indicators. These ones are just going to tell me which of the observations of the data set do I sample. And when I choose the distribution of these guys to be this, it just means simple random sampling. All observations are equally likely to be included in each of these draws here. And if I construct the estimator here as summing over the small subsample I have, and then I need to scale it up so that it ends up in the same scale that this guy lives, you can easily show that when you take the expectation, you get the true log likelihood back. So notice this is unbiasedness. So we have that the log likelihood, this estimator here of the log likelihood is actually unbiased. Okay, so now in practice, this is a very bad thing to do because the elements here, the log likelihood contributions, they're gonna vary a lot from observation to observation. So depending on which data you have, if you plot just the distribution, like how does this guy actually look, you'll see that they vary a lot. So it is well known that if that's the case, then this estimator is going to have a terrible variance. So what we did in that paper instead is that we considered an alternative estimator, so which is basically that one extended with control variates. So the control variates here, the Q, I'm going to denote them by Q. They're going to approximate my log likelihood contributions. And the estimator here is going to be what is called difference estimator in service sampling, and it's just going to have this form. So notice here that we're now just estimating the second term here. The first term here is still running over all observations. We're estimating the second term. And the idea here is that if the control variate is a good approximation of the log likelihood contributions, then these guys are going to be a homogeneous population. So remember that the problem up here was that everything was very varying, whereas here, everything is much more homogeneous, and then simple random sampling is known to work. So this guy here is going to have a small variance, and this is just a constant. In that paper, we propose this estimator here, or actually a version of this. We propose to bias correct it, because notice that this one is unbiased on the logarithmic scale, but the Metropolis-Hastings ratio requires you to take the exponent. So this guy's going to be biased, and we compute a bias correction. However, this bias correction is basically not achievable because you need to estimate a term in it. So what we instead can say that we're doing is that we're doing a bias reduction. So we're not removing all the variance, but we have a correction here that removes, sorry, we're not removing all the bias, but we have a correction here that removes some of the bias. And in that paper, the results showing that if you consider running MCMC, subsampling MCMC with the estimator that we have, you're actually going to sample from a posterior, but it's going to be a perturbed version of the true posterior. And it has a total variation norm that scales like this. Now remember that M is the subsample size, and N is the size of the population, the size of the large data set that we have. So it's clear here that this error is going to go to 0 pretty quickly, right? For example, if you let the subsample grow as the square root of N, you're going to end up with an error that grows like this in the number of observations of the data set. And we're working in scenarios where we have a very big data set, so there's going to be very, very small, and we demonstrate that in a number of examples. Yes, so that's the recap of last year's talk, and now I'm going to talk I'm going to present what is actually new here. So how did we construct the control variate? So in the previous slide, I just told you that we had a control variate that was approximately equal to this guy here, but I never told you how we constructed it. So how we constructed before, so first of all, we need to know that the first thing we need is that it needs to be a good approximation, as I said on the previous slide. But what we also need is that when we evaluate this guy here, the computational cost of doing so must grow less than order of the number of data points, because otherwise there's no point in subsampling, right? Remember that we're trying to do less evaluations. So if you compute this guy in order n, it's like, what's the point of doing subsampling? So if we need a control variate where this guy does not grow as order n, if we want to achieve any speed up. Yes, so in that paper, we followed a paper by Bardenet, Holmes, and Dosset in the Journal of Machine Learning Research, and just did a quadratic approximation of the log density around some point theta star. So theta star is like a central value of the posterior, so for example, the mode or something similar. And then the control variate is just obtained as a second order. This is just a second order approximation of the log density contribution of one observation close to theta star. Okay, so it's a second order approximation here. So now, of course, if the log likelihood density, so notice here that this is the density for one observation, right? It's not the log likelihood of all the observations, just of one observation. So this one is expected to work well if this density behaves approximately as a quadratic function in the theta region that is explored by the algorithm. Okay. However, if you have that this guy is not quadratic, obviously this is not going to work, right? Because this is assuming that the thing is approximately quadratic to be accurate. The idea here is still that, okay, so if these guys are not quadratic, then at least we would expect that if we not take one of them, but if we sum up sufficiently many of them, so notice here that S is a subset of the indices of the data. So if we take sufficiently many indices and we sum over them, we would expect the sum to be more quadratic than the individual terms. Okay, and this is like basically why you would expect that the log likelihood is a quadratic function when you have a lot of data. This is the same. It's the same intuition here. So the idea is a very simple one. Is that instead of doing control variates on each individual observation, why don't you group them into groups and do control variates for the groups? So you basically, in a way, summarizing your data to go from all the n observations you have, and then you compress them to groups. So I'll show a little bit here with a little bit of notation here. So first of all, this is all the observations that we have, and I'm gonna take a partition of all the observations that I have. I'm gonna partition them into capital cal G groups. Okay, so G1 gives me the indices of the observations corresponding to the first group. G2 gives me the indexes of the one corresponding to the second group, and so on. Okay, and importantly, the union of all these indices, we get back the full data set. So this is just a way of saying that the groups are not overlapping. You take the observations and you split them within whatever many groups you decide to have. Okay, so instead of looking at, previously we looked at the log likelihood for one single log likelihood density of a single observation. We're now going to define this L subscript GK here to be not the single contributions, but the sum of the contributions in that group. So this one is the sum of the contributions, all the log likelihood contributions in that group. Okay, and then it's pretty obvious that if you want to compute the likelihood of the full data, the log likelihood of the full data, you will just go ahead and you'll just sum the log likelihood of each group for all groups. Okay, it's a pretty simple identity. So by doing this, you're left with the number of observations instead for the original number of observations that was this little n here. Okay, and you would expect that these guys here are closer to a quadratic function that the original single log likelihood density contribution was. Okay, so what you do now is that, okay, so you do a control variate for the group instead of doing it for the individual observation. And it's pretty straightforward here. So this is exactly the quadratic function that I had before, but for the group. Okay, so you see that everything here is on the group level now. And you write the difference estimator as a group difference estimator in a pretty straightforward way. So now you sum the Q's over all groups, and you just do the estimation this way now. Okay, so it's basically exactly the same we had before, but we're grouping the stuff. Let me show you the effect of grouping. So these are 4 different models that we have in the paper. So I don't want to waste too much time on going into what each of these models actually are. We're going to look at this model later in the presentation. But what I want to show you for now is that this is illustrating the effect of grouping the control variate. So the different colors here is just how many do we have in a given group. So please notice that if we decide, that's right, I need to go up here. If we decide to just keep one observation in each group, you guys follow that that is exactly what we were doing before, right? If we just have each group has a single observation, then we're back to this control variate that is not grouped. So I'm looking into the case when it is no grouping, and then I'm looking into the case, we're looking into the case here when there's 10 observations in each group, and the final one when we actually have 100 observations in each group. So this is basically showing you the relative variance. So if this one is 1, it depends that grouping has no effect. And if it's above 1, it means that grouping is more efficient. Now you'll see that the red one is always at 1. And that's because, you know, not grouping doesn't have any effect, of course. It's just like the baseline. So everything above 1 is better. So you'll see that all these red lines here go by 1. And then you'll see in these figures, what you see is that this is the variance, right? The relative variance on each, I'm just gonna see if there's a hand raised. No hands, nothing in the chat. Yeah. You'll see that the more observations you have in a given group, for all the examples, you'll see that the relative variance is better, meaning that we get more variance reduction the more observations we have in each group. And this holds for all our examples here, for all these 4 examples. Okay? Yes, so I'm gonna move on here to a second type of control variate we're considering. So you might ask, okay, so if the group control variates are still not quadratic, what do we do then? Then we can use Bayes and Coresets. So Bayes and Coreset, so Tamara Broderick visited us, was it last year or the year before that? I can't remember, but she was talking about this Coreset stuff. So the Coreset is basically a really nice approximation that you can do for large data sets. So you replace the full log likelihood, computation with a Coreset approximation. And the Coreset approximation is just a weighted combination of these contributions here. So this, the Coreset likelihood is approximating the true likelihood, and the Coreset likelihood is just this weighted sum here. And the nice thing here is that you construct these weights in such a way that many of them are zero. So if they're zero, obviously you don't need to evaluate them. So you end up speeding up computations because you know that whenever they're zero, there's no point in evaluating them because they're not contributing to the sum. Let pi hat here be a weighting distribution that approximates the posterior. And now the question is, how do you choose? How do you choose these WKs? And what they're doing in the paper is that the weights are obtained as the solution. So you compute the squared distance between the true log likelihood. So this one is a little bit of typo here. This one should be exactly the same as here. And you compute the distance between that one and the Coreset approximation, and you weight that distance with respect to how likely each of the thetas are under the posterior, because remember that this guy is an approximation of where the posterior distribution is. And you solve this optimization problem, so you find the weights here that minimizes this expression subject to some constraints that you have weights and that you cannot have more than at most m of them being non-zero. Okay, so this is just that you just use you use this Coreset idea to approximate each of these log likelihoods for the groups. And then the Coreset approximation is the control variate. Okay, so moving to the second advancement, which I call here beyond conditionally independent data. So far, what we have done is that, and what it was done during the last talk as well, is that we're using this identity here, right? And this identity actually comes from this expression here. And this expression comes from assuming that the data is conditionally IID. And with conditionally IID, I just mean that if you know the value of the parameters, you know that the distribution of this data here just factorizes as a big product. Now you take log on both sides and you end up on this side. That's an assumption that holds in many regression models. However, there are many interesting models where this assumption does not hold. So for example, general time series problems, you have dependence across time. Spatially dependent data, you have dependence across space. The last example I have here is when you estimate the hyperparameters in a Gaussian process. So if you integrate out the Gaussian process, you're going to be left with a marginal likelihood that does not factorize in this way above. Okay, so in neither of these cases do we have this factorization here. So in the talk and in the paper with the Salamone et al. Paper, we focus on stationary time series models. Okay, so in stationary time series model, we know that the data y that we observed in the time domain, they are dependent. We know so because the model tells us that. And the approach here is that instead of looking at the data in the time domain, you look at the data in the frequency domain. And you're going to look at something that's called the periodogram data. And you're going to end up computing the likelihood for the periodogram data. So the likelihood for the periodogram data, I've denoted it by P tilde here, and this is a vector, so it's the periodogram for each of the frequencies we're going to have here. So the periodogram data lives in the frequency domain, and it is obtained as, if you see here, if you look at this part here, you'll see that this is a discrete Fourier transform of the original time series data. This is a little bit of a typo here. This one should have been Y, or this one should have been X. So this is the original time series data that we have. We take the discrete Fourier transform of the thing. We take the modulus of that. So it's this one here is a complex number. You take the modulus of that and you square it. And then you scale it by this factor here. And that's called the periodogram data. Okay? What I want you to notice here is that the periodogram data does not depend on the parameters of the model. It's just a function here of the data. Okay? And you do this for the Fourier frequencies that I have in this omega here. So then by some asymptotic properties, the elements in this vector here just collects all of these guys, are going to be conditionally. So conditionally, given the parameter, they're not going to be conditionally independent. So when you take the probability, so the likelihood of those guys, it's going to be a product over all your frequencies of the likelihood contributions of each one of them. And when you go to the log scale, you see what you have on the right-hand side here. So if you see here, what is special about this? It's a sum, right? You see that it's a sum? So before, we know that as long as we express things as a sum, we know that we can subsample. So while if we didn't do this periodogram, if we would just consider the likelihood, the log likelihood of Y in the time domain, it's not a sum. But you bring it to the frequency domain and it's a sum. So you can subsample. Yes, a little bit further details here of this, how you actually do this, is that, okay, that I said we're going to utilize some asymptotic properties of this periodogram ordinates. So you can show that for a number of frequencies here, this asymptotically, the periodogram ordinate for the omega k frequency is going to be an exponential distribution with an expected value that is the spectral density. So what you have here is the spectral density, and the spectral density is just the Fourier transform of the covariance function. So the covariance function here, we are assuming here that that the data here is zero mean, and this is the covariance function. So that's the spectral density. So the Whittle likelihood from this paper here is just, it's derived using these assumptions here. So asymptotically, you can also show that these guys are gonna be independent for each of the frequency components here. So you're gonna end up with a sum or with a product, and you take the log and that becomes a sum. And these guys here just comes from the fact that these guys here are exponentially distributed for these frequencies here. So this is how you define it, and this is the object we do this sampling on. So nice thing here is that all these derivation with the log likelihood, they rely on large sample properties of the periodogram. And that's nice for us, right? Because we actually have the scenario which we have a large M. So it's nice that the derivations here are done under exactly the scenario we're working in. I'll show you an application of modeling Bitcoin prices. So maybe like the first model you would turn to when you do the Bitcoin prices is Garch, a Garch 1.1 say. But we cannot handle Garch at the moment. Perhaps we'll do that in another paper. But there's another model here that's, to the best of our knowledge, it's the first time these two models are combined. So it's going to be an autoregressive tempered fractional integration moving average. I'm going to use this long abbreviation here for a stochastic volatility model. So in this paper, Subsampling, they propose this process here. So it has a little bit of a complicated form here, but let me just talk you through it a little bit. So you guys doing time series, you probably understand this notation directly. But for those of you who are not, let me just spend a little bit in explaining it. So we're going to have some lag polynomials here, some lag polynomial functions here. So these guys here are just the lag operators. So whenever you apply this guy, the L to the power of K here to the data, this means that it's lagging it. So you just assume that the mean is 0 here. And just to simplify stuff, what this guy's doing here is that's computing lag of the Y's, and the other guy here is computing lag of the noises. Okay, so it's like a sort of a moving average here for the noise and an autoregressive for the observations. And then we have this funny operator here, this delta operator here, which is a tempered fractional differencing operator, and it has this quite complicated form here. So the interpretation here is the D here is the fractional integration parameter, and lambda is the temporal parameter. So if this lambda here is 0, you have a long memory process. The long memory process, like the covariance function, decays so slowly that it's not, when you sum them with the absolute value, it's not converging. So it diverges. That sum diverges. If you let lambda be bigger than 0, you get what you call a semi-long memory process. So it behaves like a long memory process with some lags, but then it dies off. So this dying off makes that the sum is going to be finite when it dies off. Okay, so this is the model we're going to consider. The spectral density of an ART-FEMA model. So sorry, this is part of, so we're going to consider this model, which is this one here, but we're going to consider it for a stochastic volatility. It will be clear in just a second. In that paper, they derived the spectral density. Remember that if we want to write up with a likelihood, we're going to need the spectral density. So the spectral density has this following form here. So these are the autoregressive parts and the moving average parts. Seems that it's lagging a little bit, but yeah. In any case, so the stochastic volatility model, so in a general stochastic volatility model, you would just write here that your data YT follows this form here. When you have that the size here or an IID zero mean sequence with unit variance, and you'll have that your VT is a stationary process. So like I think that maybe the most vanilla stochastic volatility model is when you allow the VT here to be an autoregressive one process, right? That's when you get your stochastic volatility, your standard stochastic volatility one. What we're gonna do is that we're gonna allow this guy to be an ART-FEMA process, the one that I presented in the previous slide, okay? So the SV model can be estimated by using the logs here on both sides, and we introduce a new term here, epsilon t. That's going to be an IID zero mean with some variance here. So because it's white noise, it's going to have a spectral density that is of this form here. Now we can use an Artfima process for the VT here, as I said. So the combined spectral density for a model is going to be the spectral density of this guy, which is here, plus the spectral density of the Artfima process, which is up here. Okay, so I spent a little bit of time in explaining this model because it's actually quite complicated. So let's move on to the results. So first of all, just note that this is a very challenging model. In previous work in subsampling MCMC, we have been dealing with logistic regressions and other like Poisson regressions and like reasonably simple regression models, whereas this one is, I would argue, definitely not an easy model to do subsampling on. That's the first thing I want to say. And then I also want to say that we fitted an Artfima SV11 to 1 million observations. So there's actually 1 million observations here to fit this model. We use a data set, Bitcoin returns, and this is the source where we get the data from. So what I want to show you here first, how accurate the results doing subsampling are. So these are just marginal posteriors of all the parameters in the model. The black line here represent MCMC. So this is MCMC just without any subsampling. So we're still using the wavelet, but we're not doing any subsampling. And the other ones are when we do subsampling. So it's with different control variates. So you will see here that the group tends to be a little bit more accurate in all these examples. And the reason for that is that this particular example, the Coreset control variate actually has a little bit of more variance. And the error is a function of the variance. So the more variance you have, a little bit more you'll get. Okay. So what we will look at is a measure that balances both the efficiency of the MCMC chain, but also the cost of evaluating the likelihood. So in terms of efficiency, you can never be better than just using the whole data set. However, using the whole data set will give you a penalty in terms of the cost. If you start subsampling, you will lose a little bit of MCMC efficiency, but you're actually gaining on the cost, right? Because it's gonna be a smaller cost. So you want to combine these two in some way, and this relative computational time measure is actually doing that. I don't have time to go into details how we actually define that, but just think that this is number, and when this number is bigger than 1, it means that we are better than the full data MCMC by a factor RCT. Okay, so if this is 10, it means that we're 10 times better. So here are the results. So for the Artfima SV model, control variate, you'll see that we're about 100 times faster than using the full set. And the green one is the Coreset control variate. So first of all, that is not as fast as good as the Taylor control variate, and that has mainly to do with that it gives a variance. We have MCMC efficiency, but mostly because it's actually a little bit more costly to compute the Coreset variate. In any case, it's bigger than 1, so you still gain more doing the Coreset, and the Coreset might have better results when you have more complex control variate constructions that you need to take care of. Okay, so before presenting advancement 3, I think I wasn't clear enough with when you actually have the periodogram data. No, I think I was clear on that. So we only compute the periodogram once. Like periodogram data is just computed once. It's not that it's computed for every new parameter value that we want to evaluate for, because that would be, you know, we wouldn't gain anything in that case. Just wanted to be clear with that. And the last advancement I'm going to show you is this advancement that emerged during a revision. So our paper told us to compare our results against the zigzag sampler. So the zigzag sampler is a paper that was published in the Annals of Statistics. And I'll tell you just a little bit about the paper. So the paper that I presented last year, the one that was published in JASA, that has the total variation norm error, as I explained earlier. We have another paper that's an alternative approach to this paper that we use for exact inference. So notice here that I'm putting a quotation marks here on exact, because on exact inference, I hope that I just saw a colleague that's supposed to be looking at this, just coming to my room. I'm not sure if it means that the whole thing just died or if he just got tired of my talk and left. I'm not sure. Just give me a second. So I'm still talking. Did the talk die? Oh, okay. Yeah. There's. Oh, okay. I missed this whole thing. It seems that a lot of people cannot hear me. Yes, it's fine for Kerry. It's fine for Kerry Mengesen. So at least I'll have one person. Tim, can you jump in and say if I should interrupt this or what I should do? Tim? Oh, okay. So to me, I'll go until I'm supposed to finish, because I know that, yeah, so I at least have Kerry and then Stephanie Clark as well. So, Mingog, yeah, that's good. I have an audience of at least 3 people. You guys can come in and listen to me here if you want to hear the last part of the talk. Yes.
I suggest you keep going, Tim.
The results I'm presenting here are a revision, and it was when we compared against the zigzag sampler. So what I mean with exact inference in this setting is that we can estimate any expectation with respect to true posterior density to any desired precision. Yeah, Tim. Yeah, it's not just Tim. So it's Shurab, do you hear this? Okay, so I've just interrupted. So it's good for Matt 1.
Matias, it's being recorded, so you might as well keep going.
See anything on the screen?
Yes, I can hear you.
Shurab, what do I do?
Hello, Matias.
Yeah. That's actually a very good point.
I think, yeah, because it's recording.
Yeah. Yeah, okay. I'll just keep going. Okay. Yeah.
Oh, yeah. It's now
yeah,
showing that the internet connection is unstable. So.
Yeah. Okay. I'll just conclude this talk with the final advancement, and then those who are interested will just.
Yeah.
Yeah. So the internet connection is unstable. I'll just record this, and we'll just hope for the best. I just have one advancement left. Okay. So.
Yeah, we will send them the recording.
I'll just go for it. Okay. So with exact inference, what we mean in this paper is that we can estimate. Sorry? Oh, I'm out of water as well. With exact inference, I just mean that we can compute an expectation with respect to the true posterior to any desired position. Okay, so of course we do this by just using more draws. So note that that's why I'm putting it on quotation marks. I'm not saying that I'm simulating from the true posterior distribution. The only thing I'm saying is that we are able to compute expectations with respect to the posterior distribution up to an arbitrary accuracy. And the Birkens et al. Paper, they have proposed a sampler called the zigzag sampler, which is a continuous time piecewise deterministic multivariate Markov process. And the cool thing about this sampler is that you can combine it with subsampling and set it up to actually obtain samples from the true posterior distribution. So it is actually exact. Note here, I'm removing the quotation marks. You actually have, you're simulating from the distribution that you want to simulate from. So their algorithm requires some computations that involve bounding the derivatives of the log posterior. So when those bounds are not tied, the algorithm is, if you have a looser bound, it results in a more inefficient zigzag sampler. So to test how this algorithm scales with respect to the dimension, we just increase the dimension, because if you increase the dimension, you're also going to get looser bounds of these quantities that the algorithm use in its implementation. So we're testing this using a logistic regression on the well-known Higgs dataset. So the results are in this figure here. So first of all, the abbreviations here. BP is the block Poisson. That's our algorithm. ZZ is zigzag. So they have two versions. One is without subsampling and one is with subsampling. So the blue one is the one with subsampling, and it's also using a kind of control variate. So that's the CV form. So what I want you to notice here, or what I want you to know is that on the y-axis, we have the measure effective sample size, and just don't care about what this 1,000 epoch means. The only thing I want you to notice is that all these algorithms have exactly the same computational budget. So whatever is here, just don't care about it. Just know that higher is better. So what I have on the x-axis here is that I'm increasing the dimension of the problem. I start with 2 covariates, and I end up with 22 covariates, which is the number of covariates of this Higgs data set. So what you see here is that the zigzag sampler, when it's for low dimensional problems, is just crushing absolutely everything. You see that it's a much faster than what we are proposing to do. However, you see that after a number of dimensions here, we don't lose. Like if you see our effective sample size as the parameter increases, you'll see that this one is almost, it's not constant. It just looks like this with the scale of this figure, but it's not decreasing much. It's decreasing a little bit. Whereas the zigzag sampler actually decreases the effective sample size here. So after about 15 parameters, we're actually better. And I think that on full, I think this was like a 2. And also, I just want to say that the proposal we're using for our method here is the proposal from the paper with KD as first author here. This paper was published in the Journal of Machine Learning Research. Okay, and now concluding the talk, I might just have a couple of people left. But let me just conclude it. Represent 1, variate constructions. Advancement 2, we can now tackle much more challenging models using the